Hello and very welcome back to our channel. And as you all may be experiencing, we continue to present you design, analysis, and simulation of variety of circuit in the analog, digital, and mixed mode level circuit and system design in the electronics engineering and technology. And in our previous module, we have covered few modules based on the NGSpice, which is a free open source circuit simulation software. And there, if you are new to our channel, we encourage you to refer back to those modules, which are latest on our channel, and you can definitely benefit by understanding about NGSpice and its capabilities. And somewhere in that module, we have also described it is, although NGSpice is a command-based circuit spice simulator, and it doesn't have GUI to explicitly or exclusively draw the schematic, but you can use the third-party interfaces along with NGSpice. So there is a partnership between NGSpice and some other tools where you can leverage those third-party tools to draw your schematic, generate the netlist, and then use any circuit simulator, not only NGSpice, but any other circuit simulator, whether it is free or proprietary, to simulate your spice netlist, and accordingly you can analyze the performance of your circuit. So in continuation with our series of modules of using the NGSpice, circuit simulation and analysis, we have also covered few topics on the KiCad, which is also a free open source circuit design software. Not only KiCad is used to design variety of electronic circuit and simulate and analyze, but also KiCad is known to draw the PCB of your circuit, that is printed circuit board. And so it's a very comprehensive software. As you can see on the screen, we are using now this KiCad software. And by using this KiCad software, I am going to show you how we can draw a simple circuit. For example, here on your screen, you see I am going to talk about design of an amplifier using a differential amplifier, or typically known as operational amplifier. So stay tuned till the end of this video to understand comprehensively how we can use NGSpice together with KiCad to design this circuit, analyze this circuit, and simulate its performance for variety of analysis we will perform today on this topic. So I will explain you step-by-step method, because when I was designing this simple circuit, although it is simple, but there are little complexities associated about the DRC, that is design rule check, and the simulation commands, and even picking up the components and the devices from the library and using the correct spice model, whether it is a generic model or a model provided by the manufacturer for the component and the devices. So we will cover all in this module today. So stay tuned till the end of this module to understand bit by bit, comprehensively, how to design not only simple circuits, but even the advanced one using the operational amplifier and some other components using KiCad. So as you can see, I have used one operational amplifier here. I will tell you about how I pick up all these components and the devices from the library and how I made the interconnection. And then I will also simulate the circuit. So you see here, there is an operational amplifier, which has got pin number 1, 2, 3, 4, and 5. And obviously pin number 1 and 2 are the positive and the negative pin respectively, as you can see the symbol. Pin number 3 and 4 are the positive voltage supply pin and the negative voltage supply pin of an op-amp, respectively. So it is indicated by VCC, which is a positive voltage supply, and VEE, which is a negative voltage supply. Pin number 5 is the output of the amplifier. So you can see that I have configured this circuit in a non-inverting operational amplifier mode. How? I am applying the input to the positive pin of the op amp, and I am through this resistor R1, I am providing a negative feedback to the negative pin of the op amp, and there is one resistor R2 which is connected to the ground. So if you recall your theory and your basic understanding about how op amps are studied, you can recognize and realize, oh, this circuit is a fundamental non-inverting amplifier using operational amplifier. And at the pin number 5, I have output. Pin number 1, I have input. So where is this input coming from? So pin number 1, which is labeled also as in. So you see that I have used this voltage source. It could be a DC voltage source. It could be a time varying voltage source such as V sine or cos or any other time varying waveform, even the square waveform, or it could be an AC voltage source to perform the frequency analysis. So remember, DC voltage source, if used, can be used to analyze the DC performance and the operating point of the circuit. If I use as a time varying voltage source, it can be used to understand the time domain behavior of the voltage source of the amplifier. For example, I have a sine wave at the input with the gain provided by the circuit. I will have the amplified output at the output. And finally, if I configure this voltage source as an AC voltage source, then I can understand the behavior of the circuit in terms of its body plot, which is basically presenting me the frequency response of the circuit. So we will see through simulation all these analysis in today's topic. Now I have used VCC as a positive pin. So here I have used this VCC supply. I will also explain about these complexities here one by one. So here V1 is the voltage source, VCC, with respect to ground, and VEE is also a voltage source. This is the voltage source to be configured as a negative voltage supply. So you see positive is connected to the ground and the negative is connected to the VEE. So this is minus 15 volt, this is plus 15 volt being applied to these pins. And obviously the gain provided by this circuit, as you can see from our fundamental understanding, this is the non-inverting mode. So the gain is V out divided by V in, which is equal to 1 plus R1 divided by R2. I repeat, the gain of this circuit is, since it is non-inverting mode, V out divided by V in will be equal to 1 plus R1 by R2. That's the standard formula. So R1 is 1K, R2 is 1K. So the ratio R1 over R2 is 1 plus 1 will be 2. So if I apply 10 millivolt signal, I will have gain of 2, 20 millivolt amplified output. If I apply 100 millivolts here, I will have 200 millivolts right here. So we are going to actually verify it by simply plotting the waveforms. So before that, a very important point, which I actually kind of took time to make this circuit work, is that we are using the KiCad. So I will tell you now how I picked up these components from the library and how I assembled them together in order to make this circuit error-free. And then I went for simulation. So we'll see that step by step. So as you can see right now, first I have downloaded and installed KiCad software in my computer. So when you open the KiCad, the very beginning screen that you see on your computer is like this. Okay, so I just click the KiCad. After download and installation, I have this screen open, and then I click the file. Then I click the new project. After clicking the new project, here I give the name like ABC, something like that. And I can choose any directory, for example, my files, KiCad or anything right here. And then I say, okay, save. So once I save this, you see now there are two files automatically that is created, abc.keycad underscore SCS schematic and abc.keycad underscore PCB. So it means I am giving the options of creating the schematic, and then again, then I can proceed for PCB. So what I'll do, I will double click this, and after double clicking, I got this very open screen on my computer. So I am in this, I'm designing a circuit now. I can start, and then here is the symbol which says add symbol, and then I clicked here. So when I clicked here, you can see that KiCad takes a little bit of movement, and it opens the library where I can choose symbols, and there are about 21,000 items that has been loaded here. So depending on whether I want voltage source, current source, ground, power, amplifier, BJT, FET, resistors, capacitors, whatever I want, I can type accordingly, search for it here, and I can then go for it. So I did the same thing. So let me cancel it. Now I will show you through my example. So I will close there. I will type KiCad, and here is, I have version 8 also and version 7. So I will take the advanced version, and now you can see that it has opened this KiCad software again. So just recently, I have shown you how I created abc.keycad schematic. So what I'll do, uh, in the beginning, we have also designed the amplifier circuit. So we will just click, and instead of new project now, because we have already created that, so we'll ask it to open the project or open recent. So open recent is, for example, this my files op-amp differentiator. This is the name. Actually, it's not a differentiator, it is an amplifier, but I have given this name. You can give any name for that, or simply go for open project. So after opening the project, you can see that, go to my files KiCad. This is my folder name. You can give any other name, and here in this folder I have this folder, and then I have this file, KiCad project. I will just click it. See, all files have been loaded, and there are backup files over, but I'm interested in the schematic file, which I will double click. And after double click, I see that the original circuit that I have designed, I have loaded again. So I want to zoom to fit. So I click here and see whether it is what it is. Zoom to object. So I click here, and look, the screen got a little bit schematic appeared well within the screen. Now, so how I did, I click here again, add symbol. So first thing I want is VCC and VEE, for example. So I will show you step by step how I did it. So it is loading the footprint libraries now, and you can do the same things. It is taking a little bit while. This is going to be a very comprehensive module explanation. You will have a very good understand to design the real world circuits. We'll talk about the models and files. So now what I wanted the symbol for the VCC. So this is my power input. So I just typed here VCC. Instead of searching 21,000 items one by one, I can simply type the name here. So VCC is there. Then I click here, okay, and look, I place the VCC here. Okay, I place the VCC here. Okay, so let me just press the escape button on my keypad of the laptop. Again, then what I want is VEE. So I show you how I found VEE. Again, it is loading the library, and now I will say VEE. So look here, this is VEE power input. So I will click here. Okay, the VEE is here. I placed here, and I place here. So I want to do that. So I will press again the escape button after placing the VEE symbol. Okay, so after placing this VEE symbol, what I can do is I can right click here and look at this. What I'm going to do, I will use this section to kind of have it, let me select it properly. And if I do that, I want to mirror it actually. So let me see it. Okay, transform selection, and I can rotate counterclockwise, whatever. So for example, mirror vertically. So look at this symbol. I can just have it and placed it here. I placed it here. Okay. So again, I press escape button, then I select this and I press delete button on my keypad, and just I am showing you how I'm calling all the components labels on the KiCad screen and how I will make the interconnection. Next step, I want the DC power supply, DC voltage actually. So V1 and V5. So what I'll do, I'll go here again. I have clicked the component library, and here I see the VDC. What is VDC? It is the power symbol again, but I want the voltage source actually. So what I'll do is I will say source, and here I have like look, because I have already placed those voltage sources, so here I have got it. But in case you are doing it first time, so you may not have these already placed symbols for the source and all that. So for example, here is the VDC. So in that case, what I can do is here, after I search the command source, I will have this kind of attribution. So B source here. So here I will see where is my VDC, that is DC voltage source I want. So do I see here I got the current source DC. Okay, look here, I got this voltage source VDC. So after that, I just select and I placed one here, I placed one here. Okay. And once that is done, I can press escape button on my keypad, then select it again, press delete button on my keypad and get rid of it. So after that, I made the interconnection through the wires. Where is the wire? Here is the add wire. I can simply click here, from here to here, anywhere I want to connect, I can do that. So I have done that. So press escape. Now, if I do the, what I need a common ground here, just like here, then I have ground here, then I have ground here. And there you see there is the zero symbol. There is the zero symbol, there is the zero symbol. So what I'll do, I will place the add symbol again. And then here I will simply type 0. So it says me, you can have, it is also power input, which is 0 volt reference potential for simulation. Okay, this is 0 volt reference potential for simulation. So I want it. So I will click OK, and look, I placed one here, I placed one here, I placed one here. Okay, so again, I press escape button. I'm just showing you how I did it step by step. Now, I connected VDCs to the VCC and VEE, then I placed the ground, and that is 0 reference, and I placed that. What is this PWR underscore flag? So it is basically inherent or required in KiCad, unless you place this special symbol to your power sources. So for example, one I placed to the VCC, one I placed to the VEE, and one I placed to the 0 potential, that is the 0 ground reference. Okay, so unless I do that, I will not be able to clear the ERC, which is like error rule, electrical rule checker. For example, let me show you what I can do. For example, if I delete it here, and if I delete it here, or maybe I'll just show you one, because it is applied to every other thing. So let's say I don't have power flag for VCC. Okay, and then I have done all the schematic and connected, all the things are there, and now I want to make sure that after placing all components and the devices, my circuit is properly connected and it is error free. So here is this symbol, which is electrical rule checker. It performs electrical rule check. I will click here, and violations ignore test, and I will see that it will check for error and warning. So I will simply run ARC. So you see now I got the error highlighted. It says the error, that is one error, input power pin not driven by any output power pin. Okay, so that's the error. So if I click here, so clicking on this item to highlight, it will highlight me this error here. So it says that input power pin is not driven by the output power pin. To elevate this, to remove this error, I need to go to symbol, add symbol library, and then I will say PWR simply. And this is the special symbol for telling error rule check where the power comes from. So I have to tell the ARC where is the power, and here is the symbol. So you will see, click OK, and then I will place it somewhere here. And let me place it here, and then I will click the wire, and then you see that I have connected it here. So once that is connected, I press escape button to get rid of wire. Now this error will go or not, we'll see in a moment. I will do it again. Click the ARC and run ARC, and wow, good. Error is gone. Error is gone. So close it. Similarly, you have to place the PWR underscore flag symbol here and one here. If you don't do that, you you definitely end up with the error. Okay, so now you see that. And let me do it once again. Run ERC, no error and no warning. So definitely we are doing it a real world design of the circuit. So this section is finished now. What about the operational amplifier? And I will also show you how to place the values and all that. So let me first show you. I will double click it here, and here I will say I want 15 volt or 10 volt, whatever. So I have chosen 15 volt of this value. I will click OK. Then here also double click, and here also I have chosen 15 volt of this voltage source. So all these attributes you can read this. We don't need a simulation model for the voltage source actually. And then what I need is this another voltage source, but this time it's not a DC voltage source. I will choose like V sine. So what I'll do, I'll again click here, add symbol, which is actually going to open me this one. And here I type V sin. Already placed here, but I have got this also. So voltage sinusoidal, and you can see some other attributes here. There are like footprints and other information. So what is the simulation parameter? It has got DC. How much is the DC voltage? If it is time varying, then how much is the amplitude? Then frequency is equal to 1 and all that. So here is that. You placed it here. Okay. You placed it here, and that's all. That's all. Okay. So now I will select it here and I clicked it here. So after double clicking here, what I want to do it is here you see that simulation parameter. Click here, you can place some values here. DC equal to 0 volt, amplitude equal to 100 millivolt, frequency is 1000. You can change whatever. For example, I want like, let's say, 2000 hertz. AC is 1. Okay, amplitude is 100 millivolts. So I would, let's say it is 150 or whatever, 10 millivolts. Accordingly, you can do that and then click OK. So that's it. Now we have done that. Now what is about these labels in and out, how to get it from? So here you see that add global label. I click here, and then I have to choose the shape. So I have typed here, let's say is it input? Yes. Is it output or no? So I have chosen input, and then I say okay, and look, this is how I just again placed it here, then right click, transform it to mirror horizontally, and I placed it here. Similarly, I did the same thing for the output. What I did here is I typed VO, and then I chose it's an output. So click OK, and I placed it here. Okay, I have already shown you how to mirror this label. So now done. Now the main component and the registers here. So I will first show you registers. Simply I want the symbols. So I clicked, and then I simply say R. And look, with only typing R, I have got register. So I click here and look this. Now here also it's in horizontal. You can mirror it, and just by right clicking it, you can just right click here and transform selection and rotate it, for example, clockwise, and then place it where you want. And then uh, after placing them, you can double click on this, and value would be, let's say, 10K, 10K here, and click OK. Do I need a simulation model for it? Let us check it. If I click here, it is using the built-in Spice model. The KiCad is using that, or especially if you want the model for a register from the manufacturer, you can select this option, Spice model from library, and then you need to upload that file. We'll see that in some other section, but right now we are relying on KiCad to use the built-in Spice model for the device register. So what is the device type? It is an ideal register right here. You can click here, and then you can choose whether it is potentiometer, whether it is behavior. So we'll just keep it. Its value is 10K, and you see now, click OK, and click OK. And here is how you got it. Okay, so press escape, select it, and then delete. That's it. Finally, you want this operational amplifier. So what I'll do, I will again click add symbol, and here I will take op-amp. So already placed here is given because I have done that. But now look, op-amp. So it says that simulation spice. This is the symbol specialized for spice circuit simulation, including NGSpice. Okay, this is a specialized symbol. So it is an op-amp. It is single pole. Not the single pole, it is just a single op-amp. So in IC integrated circuit, you can have dual op-amp, you can have quad, but in this particular case, you have a single op-amp. Node sequence is like pin number 1 is positive pin, pin number 2 is negative pin number 3 is output, pin number 3 is out, pin number 4 is V plus, pin number 4 is V plus. One thing. 5 is V minus. There is some misunderstanding probably here. Let me check it. Just a minute. Okay, so this sequence looks a little bit mysterious because pin number 1 is positive pin number 2 is negative pin. That's correct. Pin number 3 is said to be out here, but here is pin number 5, and pin 4 and 5 here, V plus V minus. So here is like 3 and 4. So if you see some kind of discrepancy, what I see here, put your opinion, or maybe you want to correct me, that in the comment section of this model, okay, and give me your feedback. But for a while, we'll just ignore it because that's what. But here, look, simulation pins. Forget about the description here. Do we have in 1 is in plus, 2 is in minus, 3 is VCC, which is like plus power pin. 4 is VEE, which is like negative power pin, and 5 is out. That's correct. Okay, so we'll see that simulation pins here. And this is the sub-circuit simulation device and all these parameters. So there is a lot of information you can understand, and there is this data sheet given by the NGSpice itself. Right here, we'll just click OK. Once it is okay, you see now the positive pin is upward and negative pin is downward in this component. But here, what I have done is negative pin is upside and positive pin is upside. So again, I right click here and I just transform the selection, mirror it vertically. So you now see pin number 2 is up, 1 is down. This is how I did it. So I will just close it, delete it, right click here. Right clicking here, you have again a wealth of information. You see now there is the reference, that is U2, value is this one. Datasheet is just, you can refer to datasheet from this one. Then description, is op-amp, single node sequences. These are the simulation pins which are aligned with the schematics involved. It is a sub-circuit type of device. And then you have this simulation name, that is KiCad built-in underscore op-amp. Okay, so exclude from simulation, exclude from bill of material, all this. Let us click this button here, simulation model. Now look, the KiCad is helping us to call the model for this op-amp from the Spice model, from the library itself. I repeat, NGSpice and KiCad is helping us to call the model for op-amp from its library. So it is automatically selected this option. So it is not using the built-in Spice model, because I think there is no built-in Spice model. If I click here and if you select here, do you see here model for op-amp? No, I don't see it here. That's why you just let the click be here as originally. Here is the file name, spice.sp. You can see in this directory also, and how to read the .sp file, .cir file, which are the netlist or spice deck for devices and components. We have also covered that in our previous model. Now, what is the model name? It is KiCad underscore built-in underscore op-amp. Okay, so you can have like op-amp dual, op-amp quad, but by default we'll see like single op-amp, because that's what we said. Now you see the parameters, the pole is 20. So in my understanding, the pole, is it like a pole frequency, because it's a low pass filter response for the op-amp, the frequency response? So is it like, I don't know, it is 20 kilohertz or 20 megahertz or 20 hertz? Probably it is a 20 hertz if it is a provide. So that's an open loop frequency. I would say the frequency and the open loop. Then the gain is 20,000. Offset voltage V off is 10 millivolt. Output resistance of the op-amp is 10 ohm. Okay, there is, click here, the code is like this. That's the Spice netlist syntax for defining the op-amp. So you see it is defined as a sub-circuit with the X. We have also covered that in our previous model. Okay, so how about pin assignment? So you see now the pin number 1 is positive, pin number 2 is negative. So it is matching with our circuit schematic actually. And 3 is the VCC, 4 is the VEE, and 5 is the out. Now look at this reference here. So simple generic model for a single pole op-amp. So this is just a single pole op-amp. Parameters are pole frequency, gain, offset, output resistance. So we are correct. That's this 20. Where is this 20? Is the pole frequency. Then you have like the output is limited to the supply voltage. Author is given there. It's a public domain model, and how it is called. So this is basically a Spice netlist. Dot sub-circuit KiCad built-in op-amp. So that's the model name. Then you have like pins, in plus, in minus, VCC, VEE, and out. And then there are parameters of this model. That is pole frequency is 20 hertz, gain is 20,000, offset is 10 millivolt. R out is 10 ohm, and so on. So we are building our good understanding about Spice model and everything. Now, any sentence preceded by asterisk sign in a Spice deck or netlist is a comment. So it will not be executed. It is not a command, it's just a comment. Add offset voltage. So we have added offset voltage between positive pin and the in off. It is a DC V off, that's the syntax. Then the gain stage with RC pole. So is the dependent source. And this is how this op-amp has been modeled actually. There are resistors, capacitors, output decoupling. Again, this is the dependent source. This is the output resistance. And this is all those things. Finally, you have diode to limit. So limit the parameter here, and then there is an inclusion of the diode model, dot model delimit. That's not focus to understand this internal model of a Spice. That's not our focus. Our focus is to use this model as a sub-circuit in our main circuit and use it for simulation. Click OK, or simply say cancel. Oh, cancel here, and then here also you just cancel it. So we are done with this. Everything is correct. I have told you, explained to you how I uh, use the components, call the components and the devices from the model library, how I call the sources, how I made the interconnection. Specifically, I explained about how to use the model parameters and so on and so forth. So it's very good going so far. Now and we have run the ARC also, and there are no errors right over here. Good. So since there are no errors, we are all set to run the simulation. So first analysis that we would like to run. So for that, we will see the simulator. We will click here. But before that, did I forget any point to explain it to you? Or I have given you full details about designing the real world circuits from the KiCad. Oh, yes, I did so, I think. So we are using the generic built-in model from the NGSpice or from the KiCad. If we want to use the model from the manufacturer for the op-amp or for any other component, then you click here and then you have to actually select that model where you have stored the .sp file, and usually you obtain that from the manufacturer. We'll see that and cover that in some other section, some other time. Click the simulator. Let me click here, show spice netlist. So it is helping you and showing you the spice netlist. Look at this, our spice netlist is ready. So what you can understand from it and what you all can do from it, we are going to see now. So obviously in our earlier modules, when we have covered NGSpice, we have explained you in 5 to 6 models about NGSpice's capabilities, its application, how good it is as a free tool to design, simulate a variety of circuits, right? So here the first line, that is a title, that is .title KiCad schematic. Then we have included this dot include, it says that you have KiCad symbols, that is simulation underscore SP. So we are taking the help of KiCad for schematic drawing, and because of that, this line comes. So that's the inclusion of all the symbols from the KiCad. Then dot save all. Then probe ALLI, probe all I, probe V of V4, R2, XU2 is your sub-circuit, which is op-amp. Then V1, R1, and all those things. So that's the commands. Here, look, V4 is your sinusoidal voltage source, which is connected between in and 0. It has a DC value of 0. And then you specified that it is a sine voltage source, which has a 0 starting value, and peak value is 100 millivolt. Frequency is 2K. And then you have like AC, then you have like 0001. What is that? So let me check out here, or we'll just ignore that. AC is 1. So when you will do the frequency analysis, you need this parameter. Then R2 is between net minus, and U2 value of it is like 1K. Then XU2 is your built-in op-amp model. Then V1 is your positive voltage supply of DC 15 volt. V5 is your negative voltage supply of DC 15 volt. R1 is also there, and dot end. So that's your spice netlist. Then here, user-defined symbols, but run simulation. But before that, we need to specify which analysis we want to do. So let us click here, new analysis. First is DC operating point. So if we want to know the voltages and the currents in the circuit, we'll do that. So let me use the DC sweep analysis, for example. So what is the DC sweep analysis like? Let me show you on the circuit schematic. Here, no. Where is the circuit schematic? Like, okay, just a moment. Let me just have it. Okay, here. The DC sweep is like operation amplifier is basically a difference amplifier. So there is a difference between the two inputs. Only the difference between the two inputs multiplied by the gain is the output. right? So if I set some voltage here at the positive pin or negative pin, there is a difference between the two. For example, negative pin is 0 at 0 volts. And if I set some voltage at the positive pin, so difference would be the as shown, this positive pin voltage minus negative pin voltage multiplied by the gain, which is like 1 plus 1 over 1, that is 2. Remember, we have a gain of 2 will be the output. So we'll see the DC transfer curve of this circuit. So we'll click here, like create a new tab containing simulation, and we'll select DC sweep and which voltage source I want to use now. Let me again show you that the voltage source that I want to select is like, there are many voltage sources, so don't get confused. Here the voltage source is V1, voltage source is V5. They are the power supplies, but V4 is my input voltage source that I want to sweep. So let me do that. Again, V4, I will use V4 here. DC sweep, click source sweep type, that is voltage source. Look, all three voltage sources are there, but V1 and V5 are my DC voltage sources for supplying power to the circuit. I have input voltage starting value, let's say I want to sweep it from minus 50 millivolt. Remember, only the small difference is amplified in the linear range of the op amp. And let's say it is like 1 millivolt. Okay, that's it. So I am going to sweep the input voltage source V4, which is applied to the positive pin of the op amp, from minus 50 to plus 50 millivolts at the step of 1 millivolt. And then I'll do the simulation. So click OK. Now look, signals to be ready to be plotted are there. But before that, I need to run the simulation. So all the signals are ready here. So I will click run simulation. And here it says that circuit KiCad schematic at room temperature. Okay, simulation seems to have been performed. That's it. It solved the problem, but now I want to plot. So what I'll do first, V in is what I want to know how it looks like. Look, it's from 0 initially, but my sweep range is from minus 50 millivolt, here is millivolt, to the plus 50 millivolt, right? And at so that's my linear sweep. Accordingly, I want the output to be seen. So V of VO, I will click here and look at this. Now, I don't know which one is the input and which one is the output. Of course, I know the red one is from minus 50 to plus 50 is my input, and the blue line is my output. So you can see that the output is amplified one is from minus 120 to plus 80 millivolt. So for example, if the difference between the two input is plus 50 millivolt, the output is about 80 millivolts. So that's the gain I am having. Okay, because there is offset voltage also. Don't forget that, right? How about here? If the difference between input and output, if the difference between the two inputs is 20 millivolt, right here, the red point, and then the output here, the blue point is like how much is also a 20 millivolt. Yeah, it looks like that. Swept. Oh, no, here, yeah, here is 20 and 20 right here. And then like 50 millivolt, then it is 80. And here, if it is minus 50, then I am having the output of minus 120 millivolts. So almost like double. So this is all because of your offset voltage and all that. So if you want to change something, for example, let's click here, simulation, not this tab, just this one. And we'll see what it goes me. And plot setup, click, and let's say show legend, you can do that. And then you simulate again. Look here, V in and V out, they have been they have come here. Okay, right click, fit on the screen. So that's it. You want to like do some changes. So let's say you have like you want to edit the analysis, like for example, let us say click here. You want to change that. Let's say, for example, minus 150 to 150. Let us say, click here and then simulate. Look here now again. So the input voltage is from V in is like minus 150 to 150, the red line, and the blue line is then you have like minus 320 to like how much it is, 300, close to 300. Yeah, 279. Good. So you see now, if you increase the input voltage range, you have this operating point like this point where both signals cross each other, coming near to the zero as compared to earlier case. All right. So here at this point, let's say the input difference voltage is like minus 20, plus 20, and output voltage difference is like plus 30. Plus 30 plus 30. So it's like the gain of 1 or something. So your op-amp is saturated on 1. Let's say you click time domain analysis now. So transient analysis. So let's say time step is like 10 millisecond, not the 10 millisecond, like let's say 0.1 millisecond, or let's say simply 1 millisecond. So plot the data after each 1 millisecond. That's what we are telling. Final time is like 10 millisecond. Initial time is 0, which is on optional if you want, and this is also optional. And then let's say click OK. Now what you have done is, let me show you through the schematic actually. Here you are using a time varying source. So what is the time varying source? DC value is 0, but time varying signal, that is 100 millivolt peak value of sinusoidal waveform with a frequency of 2K is applied. So you want to do that. So you open it again and now run simulation and see the input. Good, you see now, but this kind of not very continuous waveform because we have used the large time step. So how I do it is like, let me reduce it like 0.01, like 10 micron, and we'll see how it goes. Now look at this, the waveform, beautiful waveform has come. It has a frequency of 2 kilohertz and 100 millivolt is the peak value starting from 0. Okay, how about output? Click output. Look, such a beautiful waveform. And when 100 millivolt is a peak value of input, output is about 180 millivolts. So there is almost gain of 2, what we have designed for, right? So it's a good thing that you can actually see this waveform in a very nice way. So just fit on the screen. So you have successfully designed a non-inverting amplifier, and you have carried out the DC sweep analysis. You have carried out the transient simulation of this amplifier. So it is quite beautiful and quite helpful. And here you can understand all the simulation intricacies of it. Now come back. We'll see how if we can do the simulation response for this one. So click here, change the analysis to like AC. Now number of points per decade. Let's say I want 1,000 points. Start frequency is 0, well, not 0, let's say 1 hertz, and the stop frequency is like 100 megahertz, or let's say 100 kilohertz. Okay, and we'll see how it goes. Good. So now once that is, I'm actually obtaining the frequency response. Click OK. And here I want to plot the gain. And look how beautifully I got the gain plot. So it's a gain of like 6 dBV. And then you want a phase, you can click here. That's the phase also. Okay, you can change the color also. Let's say green. here green. Can you do that? Yes, we'll see. Yes, it is green now. Okay, so that's your body plot for the operational amplifier in a non-inverting, right? Can you just do something else? Right click, fit on the screen, and just do some experiments with that. So very good. So we have actually done that. Let me show you the tuning also. For example, I had a tune value and I want to tune this value of a register. So once that is done, I come back to simulation, and here you see now I have got this ability to tune the value. It has a value of 2K, but I can go up to 500 hertz uh, as low as possible and see the response, how it changes on the screen. Okay, so let me do that for you. So I will just have this cursor up and down. So if I choose like 1.3K, so see the gain is changing. If I choose 2K, see the gain is increasing because 9K, something like that. So it is now 2K and the gain is about 10 dBV, right? And like only for 500 ohms, I have a gain of like 3 and 4 because so I choose it like 1.25, I have a gain of 7.7. So very good. So we have successfully designed a real world circuit of operational amplifier in a non-inverting mode using the KiCAD software, and we also can call the NGSpice netlist. We know how to call this. This is a netlist. You can just save it as a .sp file. It's a spice netlist. Open the ngSpice just for a command-based software and just plot the same DC transfer curve, same time domain simulation, and same frequency response without the KiCad. So hope you found this video useful. And if you did so, click the like button, share it with others for a wider reach. Till then, wish you happy learning. Stay tuned.